Hello students, in the last class, that is in the last video, I had discussed about polygon rasterization and multiple methods which can be used for polygon rasterization. Sometimes the polygon rasterization process can also be thought of as a sorting problem. That is, whatever the pixels present in a frame buffer can be categorized or sorted as pixels inside the polygon and pixels outside the polygon. That means all the pixels of a frame buffer will come under two categories. Either they can be sorted as pixels inside the polygon or as pixels outside the polygon. The pixels which will come inside the polygon will get updated with a foreground color, and the pixels which are outside the polygon will get updated with a background color. Now, depending on this perspective, we have three more algorithms to perform polygon rasterization. Among that, the first one is flood fill, second one is scanline fill, and the third one is odd even fill. Now we'll see the first algorithm, that is a flood fill algorithm. In flood fill algorithm, as in the previous cases, we'll consider two colors. One is a foreground color, the other one is a background color. Here in a diagram, whatever the grid you are going to observe, that grid is nothing but a frame buffer, and whatever the smaller rectangles you are observing, those are nothing but the pixels. Initially, before starting with the flood fill algorithm, all the pixels of the frame buffer need to get initialized with the background color. In our application program, we'll specify a background color. So with that background color, all the pixels of the frame buffer will get initialized. That is the first step. Then in the application program, even we will specify vertices for a polygon. So by considering those vertices, first by using the line segment rasterization, here we are supposed to rasterize edges of a polygon. Before filling a polygon with a color, first we need to rasterize the edges of a polygon. Edges of a polygon are nothing but the line segments. So to rasterize line segments, we can use one of the line segment rasterization algorithm, that is either DDA algorithm or a Bresenham's algorithm. Whenever we rasterize the edges of a polygon, we are able to observe only the edges of a polygon which will look in a diagram. In a diagram, it is not visible properly, but if you clearly observe, you can see a pentagon kind of polygon which is visible over there. That is just the edges of a pentagon. How it is visible is, in the first step, all the pixels of a frame buffer are get initialized with a background color. In the second step, all the edges of a polygon will get rasterized by using either the DDA algorithm or by the Bresenham's algorithm. So because all the edges are rasterized, we are able to observe only the edges of a polygon, but inside polygon is not filled with any color. So we are able to observe background color even inside the polygon also. Then after this step, in a third step, we need to consider a random point inside a polygon. That random point is known as a seed point. Once we select a random point, that is seed point inside a polygon, the next step is we need to check the color of a seed point. If the color of a seed point is a background color, then we need to update that point or a seed point with a foreground color, because that point is inside the polygon. So all the pixels inside the polygon need to get updated with a foreground color. So we are able to observe that structure on the output. So in a third step, we need to select random point inside the polygon, and we will call that random point as a seed point, and we need to identify the color of that seed point. If the color of the seed point is a background color, then we need to update that seed point or a pixel with a foreground color. This is the fourth step, which is the first step in a flood fill algorithm. All the pixels of the frame buffer need to get updated with a background color. Second step is we need to rasterize edges of a polygon by using one of the line segment rasterization algorithm, that is either DDA algorithm or Bresenham's algorithm. So we are able to observe only the edges of a polygon, but filling is not happened. Now to fill polygon with a foreground color, in a third step, we will select random point inside a polygon. We'll call that random point as a seed point. In a fourth step, we will check the color of the seed point. If the color of the seed point is background color, then we need to update that seed point color or a pixel color with a foreground color. Then after that, this in a fifth step, we need to identify the neighbors of a seed point. for any pixel there will be four neighbors, that is top neighbor, bottom neighbor, left neighbor and a right neighbor. Once we identify all the neighbors of a seed point, again we'll repeat the same process. For every neighbor we will check the color of it. If the color of that is a background color, then we will update it with a foreground color again. But if the color of a particular point is already a foreground color, then we will stop identifying neighbors in that particular direction. In a third step, we will select a random point called a seed point, and then we'll check the color of a seed point. If the color of seed point is background color, we'll update it with a foreground color, because all the pixels which are inside the polygon need to be filled with a foreground color. Because of that reason, the seed point color will get updated with a foreground color. After that, we need to identify all the neighbors of a seed point. Neighbors are nothing but neighbor pixels for a seed point. For any pixel there will be four neighbor pixels, that is bottom pixel, top pixel, left pixel and a right pixel. By considering each pixel in a recursive fashion, we'll check the color of each pixel, that is each neighboring pixel again. If the color of a neighboring pixel is a background color, then we'll update the color of that with a foreground color. If the color of a neighboring pixel is already a foreground color, then that indicates it is nothing but the edge of a polygon. So we'll leave as it is and we'll stop identifying the neighboring pixel again and again in the same direction, because we have already reached the edge of a polygon in that direction. We don't want to update the pixels which are outside the polygon, so when we reach the edge of a polygon, we'll stop identifying the neighboring pixels and updation of a foreground color. Now the pseudocode for this process is, we are writing a function called flood fill, which is taking two values, that is x coordinate value and a y coordinate value. This x comma y represents a seed point, that is whatever the random point you are going to identify inside a polygon, that is nothing but a seed point. That seed point we are giving as an argument to flood fill function. Then read pixel is a built-in function which will return the color of a pixel x comma y. Read pixel is a built-in function which is taking a x comma y values. X comma y are nothing but x and y coordinates of a seed point. This read pixel function will return the color of that pixel as a return value. If the color of the particular pixel is a background color, then we need to update the color of the pixel with a foreground color. Now assume here we have considered the background color has white and foreground color has black. So we are checking whether the color of a pixel is white. If the color of a pixel is a white, it indicates the pixel contains a background color. So we need to update it with a foreground color. So to update the pixel with a foreground color, we are using a built-in function called write pixel. This function is taking three parameters. First two parameters are x comma y, which will specify we are going to update which pixel. So that a specific pixel or a particular pixel will be identified by x comma y, and third parameter specifies with which color we are going to update the pixel, that is a foreground color. Here foreground color is black. After updating the seed point, we need to identify neighboring pixels for a seed point. So as I said, for every pixel there will be four neighboring pixels, that is top pixel, bottom pixel, left pixel and a right pixel. So we will call again the same function recursively for the first neighbor, that is x minus 1 comma y. X minus 1 comma y is the left neighbor for the seed point. So we'll pass those values for the flood fill function again. In the same way, we'll call the same flood fill function recursively for the next neighbor, that is x plus 1 comma y, that is a right neighbor for the seed point. In the same way, we'll call the same function recursively for the next neighbor, that is a bottom neighbor, x comma y minus 1, and again the same function gets called recursively for the top neighbor, that is x comma y plus 1. This process continues until the color of a particular neighboring pixel is a foreground color. Whenever the color of a neighboring pixel is foreground color, it indicates that we have reached the edge of a polygon and we don't want to continue further. If we continue further, we are updating the pixels outside the polygon also. That is not correct. So when we reach the edge of a polygon, we need to stop the rasterization process. This is regarding flood fill algorithm to rasterize a polygon. Then Next one is hidden surface removal. What is nothing but hidden surface removal is, for example, when we are displaying multiple objects on an output screen, sometimes one object may overlap on other object, or one object may be hidden behind another object. So in such a case, whatever the object which is hidden behind another object will not be visible to a user. So if that object is not visible to a user, then it is waste of processing that object, because anyway the user is not able to see that object on an output screen. So it is better to remove those objects from processing, so that we can reduce our processing time of a graphics system. Hidden surface removal is nothing but, sometimes when we want to display multiple objects on an output screen, some objects may overlap on another object, or some objects may be hidden behind another object. If some of the objects are hidden behind another object, then such object will not be visible to a user. If the objects are not visible to a user, then it is waste of the graphics time to process such an object. So we need to remove those objects from processing, so that we can reduce the time of processing of a graphics system. That is known as hidden surface removal. For hidden surface removal, we have two approaches. Those are object space approach and a image space approach. When we consider an object space approach, that is, in an object space approach, here we are considering two polygons. When we consider two polygons or two objects to display on an output screen, then we will have four possibilities totally. In the first possibility, B may be completely hidden behind A, so it is possible to display only the object or the polygon A. That is the first case. In the second case, A may be completely hidden behind B, so the user is able to see only the polygon or the object B, but not A. In the third case, A and B may be completely visible on an output screen, nothing will overlap on another, or nothing will hide behind the another. Then in the fourth case, A and B may be partially visible to a user. That means one polygon is overlapping on the another polygon, so part of polygon A is visible to a user and some part of the polygon B is visible to a user. So when we consider two objects to display on an output screen, these are the four possibilities which may arise when we try to render these polygons or object on an output screen. Then what is nothing but object space approach is, in object space approach, we need to consider k objects. K may be any number of objects which is greater than 1. So when we have a k object, we need to compare each object with all other objects we want to display on an output screen. For example, if we consider k value has 4, take the first object, compare it with all other 3 objects which we want to display on an output screen. So when we compare, we'll come to know how much part of a first polygon will be visible to a user. Then in the same way, compare the second object with all other 3 objects, so that we'll come to know how much of second object will be visible to a user. Depending on that information, we will come to know which object need to be stopped from processing and which parts of the object need to be processed to get display on an output screen. This comparison of object need to be continued until and unless all the object will get compared with all other k minus 1 object. Because we'll compare each object with other objects which we want to display, the complexity of this object or object space approach is 0 big O of k square, because the comparison will be performed for every object with all other k minus 1 object. The complexity is more, that is big O of k square. When we compare, we'll come to know how much part of a particular object is visible to a user. So we are going to process only that part of a polygon or an object, and remaining part will leave it without processing. Or sometimes some of the object may not be visible to a user at all, they'll be hidden behind another object, and even such objects we can remove from processing. Then the second approach is the image space approach. In a image space approach, we are not going to compare one polygon with all other polygon or one object with all other object. Then how can we perform hidden surface removal is, here whatever the grid we are observing over here in a diagram is nothing but a frame buffer or a display system. We need to generate array and that is a ray from center of a projection through every pixel. Starting from the first pixel, we need to generate a ray from center of projection through every pixel of a display or through every pixel of a frame buffer. When we generate such a ray towards the object, that ray may intersect with the objects which are in consideration. Consideration is nothing but those objects we want to display on an output screen. In a image space approach, we are not going to compare one object with all other objects. Instead of that, we are going to generate a ray from a center of projection through every pixel of a frame buffer towards the object of consideration. Objects of consideration is nothing but the objects which we want to display on an output screen. Center of projection is nothing but center of a camera. This is a virtual camera because in the graphic system we don't have a real camera. We'll assume that there will be a camera. Then whenever we generate such a ray, then that ray will intersect with some of the object or maybe one object at least. Whenever a ray intersects with object, then we need to find the closest intersection. Whenever in this example, for example in this diagram, the ray intersects with all the object, but the nearest intersection is with respect to the polygon A. That means out of all three polygons which are present over here, with respect to the pixel where the ray passes through, in that pixel only polygon A information will get updated, and we are not going to update polygon B and C because with respect to that pixel, B and C are hidden behind A, so they are not visible. So in the pixel where the ray is passing through, in that pixel the closest intersection will be with respect to polygon A. So information of polygon A will get updated in the corresponding pixel, and other two polygons information will be discarded because they are not visible with respect to that pixel because they are hidden behind A. This is the procedure we will follow for every pixel which is present in a frame buffer, and the closest intersection polygon data will get updated in the respective pixel. Then the fundamental operation is the intersection of rays with polygon. Then if we consider n cross m display, that means in a display if we have n rows and m columns, and if we consider k objects to display on an output screen, then we will carry out this operation, that is intersection of rays with polygon operation, n m k times, which will give a complexity big O of k. In the object space approach, the complexity of big O of k square, but here we are using a different approach, so here the complexity get reduced to big O of k. This is regarding hidden surface removal.